So 5.10, preparing insoluble salts. Now, insoluble salts are prepared by a method which we commonly call precipitation. So that's why you have this key definition over here. And here he's going to tell you whether the two outcomes which actually result in the formation of a precipitate or the insoluble salt. So the sudden formation of a solid in a reaction is known as precipitation, and the solid itself is known as precipitate. Now, that precipitate is usually written in as a short form as PPT, and this short form is pretty common in papers as well. And you can write it in papers too, because this is quite a commonly used short form for it. Now, there are two possibilities. The first one is when solutions are mixed. This is the one we're going to use most. The second one is only used for one scenario when a gas is bubbled into a solution. Which scenario is that? I'm going to clear it out for you. There is only one reaction. So I would really appreciate if you have the hard copy of the book in front of you and you write the direction right over here. So this is when we pass carbon dioxide gas through lime water. So this is the lime water solution, aqueous solution. When we pass carbon dioxide gas through it, what happens is that this forms a suspension of this solid along with water as a liquid. And that's the reaction. So this is the white precipitate which is formed, and this total thing has a milky appearance. I mean, this whole,
Sir,
yes,
can you just give me a minute? I'll quickly bring the pencil. I forgot it.
sure, not a problem. So getting back to it, that this white precipitate in the presence of water shows an overall milky appearance. I hope you remember it. We have already studied it as a part of 5.5, I believe. Well, write this equation first. When you're done, let me know. I'm going to clear all of this up. I'm going to take you a few pages back and you'll see which page of which exact topic I'm talking about.
Done, sir.
Okay. So if I go a few pages back, currently we are at page number 141, and I'm going to move about 8 to 9 pages. This is 5.7. The topic is acids, alkalis, in chemical analysis. This is page number 100 and This is page number 134. This is the diagram. It's showing that we are taking dilute hydrochloric acid with an anti-acid tablet or antacid tablet, and it's producing carbon dioxide gas, which we are passing through a lime water solution, which is basically calcium hydroxide, and it is turning this colorless solution into a milky or a cloudy experience. On the top of this page, on the right-hand side, this test is given, and whether it turns milky or the term that this book has used is cloudy. So if the lime water turns cloudy, the gas is carbon dioxide and the substance is a carbonate. So this is the test that we are already done with in 5.7, and you are going to see this test again in chapter number 12 as well. So this is one of the precipitation reactions in the only scenario in the book where we pass the gas through a solution, it precipitates and give you a different appearance. So for the second possibility, we have only one scenario. For the first possibility, we're going to discuss some cases. Now, choosing a method of salt preparation is very important. If the method is reactive enough to displace hydrogen in the acid, if it is, it's too reactive and therefore unsafe. So if is the base or carbonate soluble or insoluble? If it is insoluble, yeah, we have a different message. If it's soluble, we have a different one. So this is the whole thing which gives you an idea what we can actually use. Now, consider we're going to start. Does the matter react with acid? If it does it react safely? If it does, then what do we do? we go with prepare the salt by using excess metal and acid, followed by filtration, and so on. Salt can be prepared. If it does not react safely, then is the base or carbonate soluble? If it is soluble, we go with the titration method, method B in the previous portion that we have already studied. If it's not soluble, we can carry out method A, which is basically crystallization, salt reacting with acid, excess of solid, filtration, evaporation, drying. The whole process goes. So you cannot either write followed by filtration or you can write followed by crystallization. If you write filtration, you will have to write this evaporation, crystallization, which is written in this box. So that's how it works. So we need to understand which method we are going to use for the preparation. Both of these are method A's and this one is method B. And this is whole thing is only discussed or given for prescribed for preparing soluble salts. So if you know we prepare insoluble salts, precipitation is your only option. Now, barium chloride and sodium sulfate reacting. This is an example of precipitation. Barium chloride reacts with sodium sulfate. This is kind of a double displacement reaction. Barium is going to combine with sulfate. Sodium is going to combine with chloride. That's how these reactions proceed. So two aqueous solutions are mixed and they literally exchange their anions and cations. What happens is that one insoluble salt, which of course is solid, and one soluble salt are produced. The insoluble salt is something that we are interested in. So we combine its ions in an ionic equation. That's the way to write its ionic equation, right? Whichever one is solid, consider that one and separate those ions to write its equation. Get the point?
Yes, sir.
Remember, we only do it for the insoluble salt. Why do we not do it for the soluble salt? It's just that the soluble salt is a collateral product. We can safely call them spectatorines, and spectatorines are something that just simply combine and form another salt, the salt which we weren't interested in the first place. How do we separate this one out? We can always filter. This one is going to stay on the top of the filter paper as a residue, and all of this is going to pass through easy enough. It's pretty easy to go with precipitation reactions and also separate out the precipitate. You can from there on onward wash the precipitate, filter and dry the precipitate. Another reaction, silver nitrate reacts with sodium chloride. No, silver chloride is the insoluble salt. So this one is the soluble salt. Mix these ions for the ionic equation. But sometimes students ask me the question, how would we know whether a salt is soluble or insoluble? Now, this is something that we are already done with. I'm going to again go a few pages back. If you go to the pages where we discussed the salts in 5.8, you're going to see that we have a big table on the side of the page. This is page number 137. The table on the top discusses specifically which salts are insoluble. So take a look over
Yes.
there. This is the silver chloride we just formed in a reaction. This is the barium sulfate we formed in an example before it. So yeah, we know which salts are going to be insoluble, right? So for one of those salts, if the example is taken, that's how you solve it. Now, there is one tricky way the examiners ask this question in Cambridge, and that tricky way can easily be handled. That tricky way can be considered as a question for paper 2, 4, or 6, means it can be a part of MCQ, it can be a part of theory paper. Most probably, or what we have seen in the history of Cambridge, is that they usually consider it for the practical paper, paper 6. Whatever paper is that, they usually tend to ask you that you are supposed to form any insoluble salt. Let's say you are supposed to form calcium sulfate. Okay, so this is what you're supposed to form. Of course, it's going to form one aqua salt over here, and you are supposed to dissolve two aqua salts over here, two soluble salts. That's how precipitation goes. They're going to ask you what you are going to dissolve. They're going to ask you what would this or this P? Now it's pretty easy. Divide the salt up into two ions. Of course, one of the ions would be a part over here and one of the ions would be a part over here. Now, the rest of the ions is something which are spectator ions, and you are supposed to come up with those ions. Now, let me clarify. What are your options? For positive ions, I always tell my students to either use Na or K positive, which means you can either write Na over here or K over here. Since this is -2, so we are supposed to write a 2 over here, and I'm going to erase this -2 so that you don't get a problem. So sodium sulfate. So sodium or potassium ions are the best positive ions. Why am I picking these ones? I am sure about them that all of their salts are soluble. So all sodium salts are soluble, all potassium salts are soluble. That's why I picked it up. I would know for sure that this would get dissolved in water. Make sense? Now, if I
Yes,
look
sir.
at the table again, I see that this negative ion is sitting right there, making all of its salts soluble. So nitrate is going to be my negative ion option. Now for nitrate, this is negative, this is positive 2, so it goes right over here. So I'm supposed to write this 2 over here. Let's erase the other signs. There you go. Okay. So for the negative ions, always consider nitrate ions. So if you're supposed to make this insoluble salt, calcium sulfate, combine calcium with the negative ion, nitrate, combine sulfate with the positive ion, either one of them, either sodium or potassium, and that's how you're going to wind up with these spectator ions or aqueous salt over here. There you go. You have the complete equation. This is
Yes.
something which usually Cambridge plays as a question. And if you know what positive and negative ions you can start with, you're always going to end up in writing a correct equation. I hope this example is clear enough, right?
Yes, sir.
As soon as you're done noting it down, let me know. We're going to clear it up and we're going to move back to the original pages of precipitation reactions.
Done, sir.
Okay, great. So moving back to the precipitation reaction pages, that's all for the precipitation reaction topic. Let's move on. 5.11, last topic, strong and weak acids or strong and weak alkalis. Start with strong and weak acids. When we say the word strong and weak acid, we're definitely not talking about the concentration. Concentrated and dilute are the systems in which refer to the relative amounts of the solute and the solution. Well, if we use the word strength or strong or weak acid, we're directly talking about the potency of hydrogen ions in the acid. When we talk about it like that, it means something a little bit difficult. So there is another way of doing it. If I talk about strong acids, I usually going to come up with the example of HCl or H2SO4 or HNO3. As soon as we dissolve them in water, they forms the positive ion. And the positive ion is actually similar for all three of them, the H positive ions. This is because of which these are known as acids. The negative ions are, however, different: chloride or hydrogen sulfate or nitrate, or respectively hydrochloric acid, sulfuric acid, and nitric acid. What we get from this reaction is that they tend to go for the forward reaction for most of the time, and they do not like to stay in the molecular form. Hence, they dissociate as soon as we dissolve them into water. They are converted into their ion. And they are so stable in ionic form, they do not like to stay in the molecular form. However, There are some acids, for example, organic acids. At the bottom of page number 144, you see the example of ethanoic acid, CH3COOH. For this specific kind of acid, the weak ones that we call it, when we try to dissolve them in water, instead of giving a straight arrow, you're using actually a reversible arrow. They give away some H positive ions and some of the ethanoate negative ions, but only a small number of molecules are dissociated into ions at any time. Most of the molecules remain intact and do not like to dissociate. I like to explain this to my students by using a little set of numbers. If I write the equation of HCl for water, HCl is going to get dissociated into H positive ions and Cl negative ions. If we do the same with ethanoic acid, and I'm going to simply repeat the equation just without the state symbols to keep it simple for myself, although you're supposed to write it with state symbol in the exams. So that is CH3COO negative. If I say that, and I guess there is a number quoted over here too. Let me just quickly find that out. The number is quoted over here. Yeah, great. 1 in 250. So I am going to quote literally very big numbers. Okay. So, and this and this. That's right. This is the stat for HCl. And if I write this stat, okay, these are the stats for HCl and for ethanoic acid in comparison. You're not supposed to write those stats in exams. These are just for your understanding. Imagine I've dissolved 10 raised to power 7 molecules of HCl in water, out of which 99999 actually dissolved in water, dissociated to form ions of H positive and Cl negative. On the other hand, if I try to dissolve the same amount of molecules of ethanoic acid into water, only a few dissociate, and approximately that count is around 40,000. Imagine this is this many, and this is so less. So that's why we call this as a strong acid. Why? This acid loves to get dissociated when they go into water. And we call this one ethanoic acid as weak acid because it really bothers to, to get dissociated when we put it in water. It loves to stay in its original molecular form. So, in order to define it properly, these are just numbers that I was using to explain you the idea. If I go up and go to the key definition, strong acids are completely ionized in solution in water. Imagine all of its ions out of 10 raised to power 7 ionized except one. Weak acids, on the other hand, partially dissociate into ions. They hardly dissociate to form some ions in water. They love to stay in molecular form, which means both strong acids and alkalis are going to completely ionize or dissociate into water, and weak acids or weak alkalis will only do it partially. I hope you get the idea now, right?
Yes, sir.
Good, great. So when I talk about weak and strong alkalis, NaOH or sodium hydroxide is the one for which I can give the example of a strong alkali. Ammonia solution, however, can be taken as an example of weak alkali. Okay, so moving on. Remember, for strong alkalis, it's an irreversible reaction. For weak acids or alkalis, the reaction is reversible. What happens to ions in neutralization? Now we understand that neutralization is the reaction of acid and alkali given a salt and water. The simplest example would be sodium hydrochloric acid with sodium hydroxide, giving us sodium chloride plus water. Now, there you can see the ions. So, sodium and hydroxide ions, hydrogen and fluoride ions, when this combines, these two on their diagonals tend to attract and attack one another, forming water. We are only left with these spectator ions, which actually form the aqueous solution of sodium chloride. So these two try to combine, and these two try to combine. Okay, that's how it happens. And these diagrams clearly give the student an idea that how another kind of double displacement happens. The positive ion of the acid and the negative ion of the alkali combine to form water, which was our main target, hence the neutralization reaction, and a collateral product of soluble salt, which are basically spectator ions, sodium chloride, are also formed by it. Make sense?
Yes, sir. Sorry, could you please repeat which process is reversible?
Process reversible in the previous topic?
No,
Is that what you're asking?
not the process. I mean the strong acid and weak acid. Which one is reversible?
Yeah, that's what I'm talking about. Weak acid is reversible in the previous topic. This belongs to the previous topic. This reversible is the weak acid. Take a look. Weak acid's equation is reversible, and strong acid equations are irreversible, single arrow. Again, strong alkali, single
Okay,
arrow,
sir.
and weak alkali is reversible or fish hook arrows, double-sided arrows as well. Make sense?
Okay, sir. Yes, sir. Thank you.
Welcome. So, if we look at it, there is another way to explain the whole thing. Imagine this one is giving away its hydrogen ion, and this one is actually accepting that hydrogen ion. From this kind of reaction, we came up with another definition of acid and base. Now, let me clarify. We've already defined acids in three ways. Something that gives you an excess of H positive ions when dissolved in water, something that has a pH of less than 7 on the pH meter or the pH detection scale, or something that can turn the blue litmus to red whenever tested with the litmus paper is what we call acid. Later on, we defined acid as something that neutralizes a base, right? But now, apart from all those definitions, we are giving you another definition. So these were all the characteristics, and we use these characteristics to define it. Another way of defining it would be acid. Sorry. So acid, a molecule or an ion that is able to donate a proton. H positive ion is considered a proton to a base. On the other hand, sorry. Okay. So base, on the other hand, is a molecule or an ion that is able to accept a proton. We have been calling H positive ion as a proton. This is something that might require an explanation. So let's explain it first. A hydrogen atom only consists of a proton in its nucleus and an electron outside. It does not even consist of a neutron. When it loses an electron, it becomes a hydrogen positive ion. What actually is that positive ion? It never had a neutron. There was only one electron, which is now lost. What are we left with? Only one proton. That's why we call it a proton, because hydrogen ion is simply proton, which is also mentioned over here, right? So this is another definition of an acid. And this definition has been asked like hardly once or twice in past 10 years papers. So this has been a rare question, which brings us to another separate topic, basicity of acids. Not all the acids are good enough to give one hydrogen ion per molecule, which brings us to this big table 5.13 on the last page of chapter number 5. And we name three different acid types: monobasic, dibasic, or tribasic. An acid that can utilize one base ion, or two base ions, or three base ions. That's what this means. Or another way of naming them is monoprotic, diprotic, or triprotic. An acid that can donate one proton, monoprotic, donate one proton. Diprotic, donate two protons. Di means two, protic means proton donor. And triprotic means three proton donor. We're talking about one molecule. Take a look. HCl can donate one hydrogen ion per molecule. Same goes for HNO3. Although ethanoic acid has four hydrogens, but only this one can be given out as H positive, so only one. These three have one hydrogen ion per molecule. If you look at carbonic acid, this is capable of giving two hydrogen ions. Sulfuric acid, two hydrogen ions per molecule. So dibasic or diprotic. Phosphoric acid is a great example of tribasic or triprotic acid. What happens is that whenever they react with a base or an alkali, and if the reaction goes to completion, they form normal salts, which is easier to understand, right? But if they can donate more than one protons, and we stop the reaction after one proton donation, we end up with acidic salts. Acidic salts are the salts which still contain hydrogen as a part of the salt. So sometimes we need to write reactions to explain it. One of the reactions from here are written on the previous page. So I'm going to take you back to the previous page. Take a look. Sulfuric acid is a diprotic acid. It can give us two hydrogen ions per molecule. And as you can see, the formula also consists of two hydrogen ions per molecule. When it is going to react with an alkali, this is going to happen in step-by-step process. NaOH is going to react with one hydrogen ion at a time. Take a look. We take one hydrogen ion out of it. It is going to react with OH and form water. What are we left with if we take one hydrogen ion out? We're left with HSO4 negative. Na is going to react with it with a positive sign. So remove this positive and the negative. This is what we have at the start of first reaction. Take a look. NaHS4. Name sodium hydrogen sulfate. It's not just a sulfate, it's hydrogen sulfate. So what happens is that it can react with 2 moles of NaOH as well. And both of the hydrogen ions will then be displaced with sodium ions. So Na2SO4, now there are no more hydrogens, and both the hydrogens have actually neutralized both the OH ions, giving you water. So this attacked the hair and this made water. Make sense?
Yes, sir.
Again, in the past papers, you have been asked this question like just once, and they ask you to write the equations for carbonic acid and phosphoric acid. So will you be able to
Okay,
write the equations for carbonic acid or phosphoric acid, or should I write them for you?
there you can write for the phosphoric acid.
Yeah, sure. Since phosphoric acid is a tribasic acid and it can form three products, and actually all three of them are mentioned on the next page, page number 147, table 5.13. Take a look. One of the products is Na3PO4. This is the final product actually. NaH2PO4 is the first product, and Na2HPO4 is the second product. Let's write the reactions for this, and we're going to use the same alkali. So H3PO4 reacts with NaOH. If it reacts with just one NaOH molecule, it is going to form. Now, how do we do it? Try to understand it. take one hydrogen out of it, what are we left with? H2PO4. And instead of one hydrogen, just write one sodium ion. That hydrogen is going to react OH and form water, so one molecule of water. But it's not necessary that it only reacts with one mole of NaOH. We may react H3PO4 with two molecules of NaOH. If that happens, watch closely what we are about to do. Take two hydrogen out of H3PO4. What are we left with? HPO4. I've taken two hydrogen out and replace those two hydrogen with two sodium over here. So it becomes Na2HPO4 plus, of course, 2H2O. Make sense? So we are done with this product and we are done with this product. Now, if H3PO4 reacts completely with NaOH, and that's going to be possible with 3 moles of sodium hydroxide, you are then going to replace all three hydrogen. Simply write this PO4, replace them with 3 Na, Na3PO4, and you would receive 3 water molecules. That's the final reaction, and now the product is a normal salt. It's not an acidic salt anymore. Normal salts are only produced when acids are completely neutralized with alkalis or bases. So these are the three reactions we need to understand from this. Make sense?
Sir, I got disconnected. Could you please repeat?
Okay. So let's start with the first equation. Now, take a look at the first equation. What happens is that H3PO4 reacts with 1 mole of NaOH. Now, how are you supposed to write it? First of all, take one H out of H3PO4. If I take one H out of H3PO4, what would that be? H2PO4. Replace with that one H with Na. So it becomes NaH2PO4. And that one hydrogen reacts with OH to form H2O. Okay? But that's not the
Okay.
only way we can react it. You have only formed this product yet. So H3PO4 can also react with 2 moles of NaOH. If that happens, take out 2 hydrogen from H3PO4. If I take out 2 hydrogen from H3PO4, the remaining formula is HPO4. And of course, those 2 hydrogen are replaced by 2 sodium atoms. So Na2HPO4, which is this product, by the way. And of course, we're going to produce 2 moles of water. There is one last possibility that I take all the hydrogen ions out of H3PO4, which are 3 hydrogen ions, which is possible if I react it with 3 moles of NaOH. In that case, take all the hydrogen out, simply write PO4, and add 3 nitrogen to it in order to replace the hydrogen and maintain the valency. It finally forms Na3PO4. It also gives out 3 moles of water. And this is the last salt we're supposed to make. If a salt does not contain hydrogen, it's considered as normal salt. If a salt consists of hydrogen as a part of the formula, it is known as acid salt. I hope now it should make more sense, right?
Yes, sir.
Great. And by this, we actually finished the chapter. Any questions?
No, sir. It's clear.